Okay, class. So, we have here a sample problem for the Carnot cycle. So, remember that the Carnot cycle is the most efficient thermodynamic cycle. So, we have here the first problem. So, a Carnot engine receives 130 BTU, which is British thermal unit, of heat from a hot reservoir at 700 degrees Fahrenheit and rejects 49 BTU of heat. Calculate the temperature of the cold reservoir. So, as you can see, we have the givens. We have the heat added. Heat added is equals to the 130 BTU. A Carnot engine receives 130 of heat, okay? It receives, so it means added from a hot reservoir at 700 degrees Fahrenheit. So in Carnot cycle, we have two temperatures, which is the high temperature and the low temperature. So it means hot reservoir and the cold reservoir. So hot reservoir, that is the highest temperature of the cycle, which is 700 degrees Fahrenheit. So we have to convert it into Rankine so that this is we have to use the absolute temperature in solving the problem. Then rejects heat at rejects heat at around 49 BTU. So this is the heat rejected. So calculate the temperature of the cold reservoir. So how can we solve the temperature of the cold reservoir? Remember class that efficiency is equals to work net over QA. But work net is equals to the heat added minus the heat rejected over QA. So QA, QR is given. Okay. But remember also that efficiency is equals to the high temperature minus the low temperature over the high temperature. So by using this formula, we will be able to solve this problem. So QA minus QR, that is 130 minus 49. Okay. 130 minus 49 over 130, which is equals to the highest temperature, which is 1160 Rankine, minus the low temperature over high temperature 1160. So let's manipulate the equation. So 130 minus 49, that is 81 over 130. So cross multiply by 1160 is equals to 1160 minus the low temperature. So let's use our calculator. So 81 minus divided by 130 multiplied by 1160. That is 9396 over 13. Okay. So we have to transpose this 1160 to the other side. So positive, it will be now minus 1160 is equals to negative temperature low. So minus 1160 okay. That is equals to negative 437. So negative 437 point 2308. 2308 negative TL. So negative, negative, that will be positive. TL will be equals to 437.2308 degree Rankine. So to change this, to convert this into degree Fahrenheit, we have to subtract it by 460. So TL will be equals to negative Fahrenheit, degree Fahrenheit. It is equals to plus 460. No, minus 460. So that is equals to negative 22.77. Negative 22.77 degree Fahrenheit. So this will be our final answer. This will be the temperature of the cold reservoir. Okay. Okay. Our next problem. A Carnot engine operating between 775 and 305 Kelvin produces 54 kilojoules of work. Determine the QA, the change in entropy during heat rejection, and its efficiency. Okay. Okay. So the problem, there are three uh, parameters being asked. So let's find the given. So what are the given in the problem? So given. So operating temperature between 775 and 305. So we have the T high, which is equals to 775 degree Kelvin. Degree Kelvin class is in absolute. So we don't have to convert it. And 305 degree Kelvin. That is the low temperature. So produces a work of 54. So we have a work here. Work is equals to 54 kilojoules. So this is work net. Okay. So determine the QA. So first we have to determine the QA. So remember that QA efficiency class. Efficiency of the cycle is equals to work net over QA. Okay. So efficiency is not given. Work net is given 54. So but efficiency is equals to class to high temperature minus low temperature over T high. Okay. So by using this relationship, we can get the QA. So work net is equals to 54 kilojoules over QA is equals to TH 775 minus 305 over 775. So let's manipulate the equation. 54 over QA is equals to 775 minus 305. 775 minus 305, that is 470. 470 over 775. So let's manipulate the formula again. So cross multiply. So therefore, we will have a QA is equals to 54 by 775 over 470. So QA is equals to 54 by 775 divided by 470. That is equals to 89.0426. 0426 kilojoules of heat added. So this is the letter A. Then we have the change in entropy during heat rejection. But first we have to find this efficiency. So efficiency is already given. So this is the efficiency. Let's try to solve this one. So efficiency will be equal to 775 minus 305 divided by 775. That is 0.6 60 65. 0.6065, or multiply that by 100, we will have a 60.65% of efficiency. Okay, this is letter C. Then determine the change in entropy during heat rejection. So in order for us to see what is being asked, let's draw the diagram. Let's draw the PB diagram or TS diagram instead. TS diagram for the Carnot cycle. TS diagram. So let's say this is the process 1. So the cycle movement is like this. Process 2. Process 3. To process 4. So what is being asked is heat rejection. So heat rejection class, this one, process 3 to 4 is the heat addition. And then process 1 to 2, that is the heat rejection. So therefore, change in entropy is equals to S1 minus S2, which is equals to, for example, was this area is the heat rejected. Okay. So this is temperature 1, which is also equal to temperature 2, or this is the lowest temperature of the cycle. Okay, so in order for us to get the area, this one, this is the Q rejected, okay? So the area, this is temperature low. So on this side, this is S1 minus S2, which is also equal here. So S1 minus S2. So length times width, that is the QR. Okay. So QR is length times width. So TL times S1 minus S2. So change and entropy is being asked. So therefore, change in entropy is equals to QR over TL. So temperature low is given. This one is given. QR is given. So we can able to find this change in entropy. So QR, okay, so QR, we can get the QR by using the efficiency. Okay, this one. So remember class that efficiency is equals to work net over QA. So efficiency is equals to QA minus QR over QA. So given QA, given we will be able to solve the heat rejected. Okay. So let's try to solve first the heat rejected. So efficiency is equals to QA minus QR over QA. So let's simplify it again. Efficiency is equals QA over QA, that is 1, minus QR over QA. Okay, let's substitute. So efficiency, let's manipulate. So efficiency will be equals to efficiency. So transpose minus 1 is equals to negative QR over QA. So QR will be equals to negative QR is equals to efficiency. Now, let's try to remove this sign, transpose the sign. So if we transpose the sign, that will be equal to positive 1. So 1 minus efficiency multiplied by QA. Okay. So QR will be equal to 1 minus 0.60 65 times QA. QA is equals to 54. No. QA is equals to 89.0426. 89.0426. So QR will be equals to calculator. 1 minus 0.6065 multiply by 89.0426, that is equals to 35.0382. 0382. 0382 kilojoules. That is the QR, heat rejected. So given heat rejected and the low temperature, we will be able to solve the change in entropy. Change in entropy, QR, is 35.0382 kilojoules. And then temperature is equals to, temperature low is equals to 305 Kelvin. Okay. Degree Kelvin. So the answer is divided by 305. 0.1149. 0.1149 kilojoule per degree Kelvin. That is the change in entropy. Okay, next problem. The maximum thermal efficiency possible for a power cycle operating between 1200 degree Fahrenheit and 225 is, so efficiency is being asked. So efficiency is equals to high temperature minus low temperature over T high. So we have here 1200 degree Fahrenheit and 225. So TH will be equals to 12 plus 460. So that we have a Rankine absolute. So 12 plus 460, that is 1660. 1660. And the low temperature is 225 degree Fahrenheit plus 460. That will be equal to 685 degree Rankine. So we will be able to solve the efficiency. So efficiency will be equals to 1660 minus 685 over 1660. That will be equals to 0.58. Or equal to 58.73%. Okay. Last problem for Carnot cycle. So a Carnot engine requires 35 kilojoules per second from the hot source. The engine produces 15 kilowatts of power, and the temperature of the sink is 26 degrees Celsius. What is the temperature of the hot source? So TH is being asked. So what is the TH? So TL is given, which is 26 degree Celsius. So plus 273, we will have the absolute value. That is equals to 26 plus 273, that is 299 Kelvin. Then, what else is given? So, we have the work net. Work net is 15 kilowatts. And then, What else? We also have the QA. So QA is 35 kilojoules per second. Remember, class, that kilowatts is also equal to kilojoules per second. So in order to solve the high temperature, we will use the efficiency formula. Okay. So efficiency is equals to work net over the QA. So these are given, which is also equals to temperature high minus temperature low over temperature high. So we will be able to solve the problem. So work net will be equals to 15 kilojoules per sec over QA, which is 35. Same units. So therefore, temperature high. So let's manipulate one. Temperature high. So temperature high, that will be equal to 1 minus TL over TH. So 15 by 35 minus 1, and then multiply by negative, no, no, equals to negative TL over TH. So we are looking for H, right? So TL is given, which is 299. Okay. So TH, cross multiply TH will be equals to TL, which will equal to 299 over 15 over 35 minus 1. So 299. So this will be also negative. So TH will be equals to calculator. So 15 over 35 first. 15 divided by 35. That is 3 over 7 minus 1. So negative 4 over 7. So divided by negative 299. And let's get the reciprocal of that. So reciprocal, ibig sabihin, baliktad. So 2093 over 4. Reciprocal, where is the reciprocal here? Reciprocal. There is no reciprocal here. This one. X minus 1, okay? Let's get the reciprocal of that. Answer. So 23 over 4, that is equals to 523.25. 25 degree Kelvin. So in Celsius, so just subtract it by 273. So we will have a 250.25 degrees Celsius. That is the temperature. Okay, class. So if there are any questions, please feel free to comment in our G streams. Okay. And just inform me immediately if you have any questions regarding this problem solving. Okay, class. Thank you for listening. And I think let's have a quiz this coming Friday. Okay, class. Good luck and thank you.